One review for math. Oh, thank you. Yes. Integral calculus, math 2414. Differentiation in reverse is integration, and we're also going to touch on vectors at the end. So if you remember from differential calculus, math 2413, there were rules of differentiation. This is actually the title for Stewart's Calculus Chapter 3, is the rules of differentiation. As opposed to now we have techniques of integration. So can anyone list some or all of these? What are the rules of differentiation? Right, we have to know those before we can do it in reverse. Okay, so what are some of the rules of integration or differentiation? Does anyone? Let's see. Yeah, the power rule, that's simple. Yeah, that's a straightforward. Chain rule, yes, that's a good one. Yes, because that's sort of like more. Quotient rule, yes. One more important one. Product rule. Yes, I would have also accepted implicit differentiation, which is kind of like the chain rule, and I would have also accepted logarithmic differentiation. Now, what are the techniques of integration? This is what y'all will be tested over. Can anyone list some techniques of integration? Integration by parts, U sub, trig sub, integration by parts, cool. Two more. Tabular is integration by parts. Two more. Think of any, think deep. Partial fractions, yes, one more. The last one I'm looking for is improper is a special case of partial fraction. I think that's what you're talking about. Oh wait, no, improper integral. Yes. Okay, that's a perfectly good one, Amir. And then also, what is it? Trig integrals. That's 7.2 in Stewart's calculus. We'll cover that extensively. So here's a list. Improper integrals, I put that, and then I would also accepted integration by tables. Y'all don't cover that, but there's integration tables, and you can solve a lot of integrals with those. Those are all found using techniques that we discuss here. Okay, so question: if a function is differentiable, can we find its derivative like always? What do you guys think? If a function is differentiable, if its derivative exists, right, the limit of the difference quotient, can we always calculate the derivative? Yeah, it's super straightforward. We could just use some of the rules and then it'll always pop out nicely. Now, is the same true for integration? If a function is integrable, can we always find its antiderivative? Maybe you guys don't know this one. It is actually, we'll see in the next slide. Oh wait, 2 slides from now. Hold your excitement, right? So if this is kind of like nullifying the hypothesis, the if. So if a function is not differentiable, we cannot find its derivative at that point of non-differentiability. Some functions that are not differentiable are integrable. Integration is it has a lot lower standard for what it allows to be integrable. I'll go on to the next slide. Oh wait, let me talk about this example. So our function f, this is not differentiable at 0, so we can't find a number or a function to represent its derivative at 0. But for the same function, I found an antiderivative expressed in elementary functions for all x. So it seems in this case, integration is easier, right? But we look at the next slide. So this function, e to the x squared, we can't express its antiderivative in terms of elementary functions. It's like a problem that we just can't do. But it's integrable because it is continuous. All continuous functions are integrable. Think about it. So continuous function is like an easier condition to meet than being differentiable. So this has a non-elementary antiderivative. Elementary functions are simply the functions that we're used to. Okay. And as a matter of fact, most functions, we just can't find antiderivatives for. Most of them. Things like e to the x squared or sine of x squared, cosine of x squared. You could try to find these antiderivatives, but no one has found them yet. So we deal with a subset of integrable functions. This subset of integrable functions are functions whose antiderivatives can be expressed in terms of elementary functions, expressed in terms of the functions we're used to. And then we can actually find approximations, but we will not cover it because it's not on your exam, to integrals like this. You could use rectangles. You could use to approximate the area, so it would have to be a definite integral. Or you could use things like trapezoids. And then there's also something called Simpson's rule, which you approximate area underneath the curve with parabolas. And it's a higher grade approximation. So what can we find these antiderivative formulas for? Well, all the problems in these sections, we can find antiderivative formulas for, right? This is just the sections corresponding to integration by parts, trig integrals, trig substitution, partial fraction decomposition. I forgot what 7.5 is. Oh, that's just strategies for integration. So yeah, everything in these sections, we can express the antiderivatives in terms of elementary functions. So don't forget, write plus c for every indefinite integral. And indefinite integrals have no limits of integration, right? If you don't write the plus c at the end, I'll get it to you somehow. Well, actually, this whole lecture will be posted on YouTube. So indefinite integrals have no limits of integration. So don't forget to write the plus c. They will count points off if you don't write plus c, okay? Okay, so now we get into the meat of it. Here I prove integration by parts. Integration by parts is a reverse product rule. It's associated with like the antiderivative of a function you would use integration by parts on. You would need the product rule to differentiate, right? So maybe this kind of like if you integrate something and then you take the derivative of something, you should get like what's in the integrand back out of it. So as a way to check your work. Now, here I prove it. We start with the product rule as it is. U times v, two functions of x, we differentiate them. We get u dv plus v du. This is just the product rule. And then I integrate both sides. Remember, the integral of a derivative, well, those just cancel. We get u times v. And then we integrate the right-hand side as well. Okay? Right, the integral can distribute over addition. Don't forget that. The integral can distribute across addition. Also, if you have a constant times a function and you're integrating it, the constant can come outside of the integral symbol. So you don't have to worry about it. That's a result of linearity. Maybe you guys don't know what that means yet, but if you take linear algebra or any other math, you'll learn, and the same is true for derivatives really, but the derivative operator, the integral operator are linear transformations. So you can distribute them across addition and you can pull out constant numbers out of them. And so this last line right here is the formula we know and love, right? I just subtracted one of the integrals over, and this is the integration by parts formula that we use. So here it is. If you have trouble remembering it, it's an acronym, ultraviolet voodoo. UV minus the integral of V du, ultraviolet voodoo. Okay. When do I use it? When do we use it? Well, when the easiest technique of integration doesn't work, that would be a nice time to at least think about it. And then also more rigorously, right? We have a product of two functions in the integrand, but this is not always the case. So here are the steps to performing integration by parts. Choose u. U must be easily differentiable. I mean, it doesn't have to be, right? We can take the derivative of anything, but choosing u that's easily differentiable, and also choose u such that dv is easily integrable. Okay? Because, right, we make that little table. We have u, du. We choose u. What's remaining is dv. So we have to integrate dv at some point. If we choose u such that dv is easily integrable, then it just makes sense to do it this way. So we calculate du via differentiation of our choice for u, and then we integrate. This should say dv. Okay, then we plug it into the formula. We'll have another integral to solve in the formula, but hopefully that's equally as simple, or at least equally as simple, but hopefully more simple than the integral we started with. So some problems do require multiple sweeps of integration by parts, right? We have to do it more than once. And I actually have a meme for this. Okay. Choosing u. There's another mnemonic, liet or ilate. I use liet because that's how I was taught, but it represents the order of precedence for choosing u in the formula. Okay. So our first choice for u should always be logs. If there is a log in the integral, we will choose logs to be u. Else, pick inverse trig. Otherwise, algebraic. Algebraic just means a polynomial or something with a rational exponent. Then if we have trig, choose trig to be u. If not, choose exponentials. Yeah. So in your expression for dv, I see this all the time. People forget to write dx with it. Dx is part of the integral. So, and we have to integrate dv. So we have to integrate with respect to something. We can't just integrate x. The integral of x, that's ambiguous. That doesn't tell me what to do. The dx, that tells me what to integrate with respect to. It doesn't matter so much right now because this is single variable calculus, but later on, if you take multivariable, it will matter a whole lot. And then sometimes you don't have anything remaining besides dx, in which case you just write 1 times dx and integrate that 1 times dx so that v equals x. Here are two examples of times where you would use dv equals 1 times dx. And these problems are actually also in our problem list that you guys will get and get to work on. Okay, so this is chapter 7.2, trigonometric integrals. So when to use it, I wrote a list. Hopefully this is exhaustive, extensive, or it covers all cases. I think it does. But if you have products of powers of sine and cosine, products of powers of secant, tangent, same thing for cosecant, cotangent. If you have a tangent or a cotangent or a secant or a cosecant by itself, this is also a trigonometric integral. Or you have a product of sines and cosines, sines and sines, or cosines and sines with multiple angles. That means like, well, you'll see. So looking at the first one, hopefully you guys know this by now, but here are the rules. What do you do when you have an integral in this form? It's sine to m. M is an integer. N is also probably a natural number, a whole number, a positive whole number, and n is also a positive whole number. So if m is odd, if the power of sine is odd, you peel off one factor of sine and rewrite this next to the factor dx. That's the first step. In the other case, if n is odd, you peel off one cosine factor so that whatever is remaining is now to an even power, and you write this cosine factor next to the dx. If they're both odd, pick your favorite. I would probably pick cosine, or actually, I would pick sine. But here's the next step. It's just a glorified u substitution. You convert the remaining factors of the trig function that you peeled off, so everything except for that lone one at the end, you convert that to the other one via the Pythagorean identity. So I solved it for you. We know that cosine squared x plus sine squared x is 1. And then in either case, right, we have sine squared or cosine squared equals 1 minus the other squared. So and then after this, you would choose u to be the one with the most powers, right? So you'll only have like one factor that you peeled off at the end next to the dx of, like, say sine, for instance, and then you'll have like a bunch of powers of cosine. So then you would pick u to be cosine, and then it would reduce the problem to u substitution. If both sines and cosines are even, there's no need to peel. You just convert one of them, which your favorite, I guess, to the other trig function, and then use power reducing formula, the one I listed right here, to reduce it until you have a single power of cosine of a multiple angle. After that, it's a pretty straightforward integral. Okay, so here are the rules for trigonometric integrals. If you have a product of powers of secant and tangent, like how I listed right here, if it's in this form, then I go through the first case first, and then I go through the second case second. So the first case, if n is even, right, if the power of secant is even, then you will peel off a secant squared factor and rewrite this next to the factor dx. Then you convert the remaining secant to tangent using this formula. The resulting integral will be u substitution, choosing u equals tangent of x. I have a question for y'all. If u is tangent of x, what is du? If u is tangent x and a u substitution, what is du? Yes, secant squared x. Oh, everyone forgot! Everyone forgot, man. The dx. Yeah. Okay. All right, so otherwise, in this type of integral, if n is not even and m happens to be odd, then you peel off this factor, secant x, tangent x. And then rewrite with, you know, the secant x, tangent x next to the dx. Then you convert the remaining tangent to secant using this formula. This is just rearranged from the last one. Like we just subtracted 1. And so tangent squared is secant squared minus 1. The resulting integral will be u substitution with u is equal to secant. So if u is secant, what is du? And I'll cut you a break. You don't have to write dx. U is secant. Du has to be, yeah, secant tangent. And oh, he's the overachiever. The dx. He wrote it. Very nice. Repetition strengthens and confirms. Okay, so if you don't want to memorize all these rules, simply do both, right? Simply try both of them, and then you'll run into a dead end in one case. And then you just know now to go to the other one. Someone raise their hand. If you have a question, either type it in the chat and someone else will answer it, or raise your voice. I guess I lowered it. Okay. Oh, never mind, IDK. All right, so yeah, I mean, you could try both methods, and really, like, I don't memorize, like, the past 4 slides. That's just annoying, right? So what I do is, I mean, to learn integration, if you really want to learn integration, you just pick up a book and try a bunch of problems until you kind of, like, internalize all these rules and you know when to use what. So going on to the next slide. Yeah, this form of integral is more tricky. It's not always a u substitution like the sines and cosines, and we'll see a problem. Hopefully we get to it with the leader, you know, in the breakout groups. But yeah, so we will see one of these integrals that requires integration by parts. Maybe you've even seen it in your homework already. Products of powers of cosecants and cotangents. Exercise for you. You guys can devise your own rule for these types of integrals. Trigonometric integrals. So if we have a lone tangent, cotangent, secant, or cosecant. Tangent and cotangent, those are pretty straightforward. You just convert it to sine and cosine first, and then you use u substitution. So in the tangent case, tangent is sine over cosine. Choose u to be cosine. Then du would have to be sine dx. Okay? And then cotangent, you just do the reverse. Secant and cosecant are found using a magic 1. What does that mean? What happens when we multiply by 1? Well, nothing. So we multiply by 1 in a cute form, a special form that helps us solve the problem. And we'll see this in the breakout groups, actually. We'll integrate, hopefully we'll get to integrating secant x dx. Okay, what if we have products of multiple angles of sines, cosines, sine sines, or cosine sines, integrals of this form? If we have integrals of any form like this, all we need to use is either the sum or difference of these 4 formulas. So really, it's either this first one or the second one. Okay? You just add the sine a plus b plus sine a minus b, or you subtract it. Either one of those. And we'll see this in the breakout groups. We'll see examples of these worked. So yeah, you basically, yeah, you just convert it into something more simple to solve using these trigonometric formulas from, you know, trigonometry, from pre-calculus. Trig substitution, right? There was a question over this before the thing got started. Do you see a square root in a rational expression? That means just a fraction with powers of variables. Is the expression under the radical in one of these forms? If this is the case, then I would bet it's a trigonometric substitution. And for one, a squared minus x squared, we have x equals a sine theta. If it's a squared plus x squared or x squared plus a squared, then it's x equals tangent theta. And then for 3, right, if we have x squared minus a squared, then you would use x equals a secant theta. And then the differentials, you just calculate this straightforward, right? You just take dx of whichever one you picked. And hopefully you know your derivatives so that you can calculate this. You don't need to memorize them. You can just calculate it every time because you already have the derivatives memorized. And then you need to draw a picture. This might come through at the end after you have integrated. And then you have like the antiderivative in terms of other trigonometric functions, in which case you just use your rule. You use your substitution and then devise whatever, like if we had this first one, right, and then we want cosine of theta. So here's theta. We take cosine of theta. Cosine of theta would be the square root a squared minus x squared over a, adjacent over hypotenuse, right? That's just SOHCAHTOA. And so, you know, in any case, you just look at the triangle if you have the antiderivative in terms of these other trig functions. Okay. You can do the same thing with hyperbolic trig. We're not going to talk about it. So if we have partial fraction decomposition, this is integrals of this form. The integral of p of x divided by q of x. So I guess you might be able to say like, oh wait, Luke, isn't some trigonometric substitutions the same as this? Well, yeah, but if you can do trig sub, then do it. Otherwise, do partial fraction decomposition. P of x and q of x are polynomials too, most of the time. We'll see an example where P of x and q of x are exponential. But it's the same sort of rules. So the most commonly overlooked step is to first check if the fraction is improper. Now tell me, someone, what is an improper fraction rational expression? How would a rational function be improper? Yes, that's exactly it. Degree top greater than degree on bottom. If degree of p of x is greater than or equal to, it has, yeah, if it's equal to as well, then that is also considered improper. In this case, do polynomial long division. I know it's probably been a while, but yeah, what can I say? What can I say? Math builds on itself, right? So the result of these types of integrals will be the sum or difference, really a linear combination of all or some of the following functions. So you don't need to know what a linear combination is, and you'll find that out if you take linear algebra. But these integrals, the answer will always be a sum or a difference up to multiples of a polynomial. And this is only when long division is required. It will usually have a logarithmic expression in it when it has linear factors. If it has any linear factors in the denominator, then you'll have a logarithm pop out. It'll have a rational expression if it has repeated linears. And then it'll have arctangent when it has irreducible quadratic factors in the denominator. And then always, we have the constant of integration. So maybe this could be an exercise for you. Prove this. Show this. The integral of dx over x squared plus a squared is 1 over a arctangent x over a plus c. It's a nice one to know for these partial fraction decompositions. And a strategy. Okay, yeah, one last thing I wanted to say about this actually. No, that's it. That's it. Strategy for integration. This is chapter 7.5 in Stewart's calculus book. Is it the integral of a derivative we already know? Like if it's the integral of a derivative, right, then we would just take the function that we would differentiate as the antiderivative. Can we apply a formula is what that means. Like is it something super, like, for instance, is it something like this? Is it something we already know? If not, can you simplify the integrand? What is the integrand? Someone tell me what an integrand is. Does anyone know what an integrand is? Yeah, under, inside, that's the integrand. Go through the mental checklist of techniques we know. So whenever I look at an integral and I first ask myself, is this a U substitution problem? Because that's the easiest. Well, actually, first, is it something I already know, like a derivative of something I know? If not, then I ask myself, is it a U substitution? If not, well, is it integration by parts? If not, is it a trig integral? If not, is it trig sub? If not, is it a partial fraction decomposition? If not, is there a table I could look at? If not, either, there's no answer to it, or invent a new method. But that's beside the point. We're not going to have anything like that, And so the last section in chapter 7 that we're going to talk about, improper integrals. So the main idea is integration over an unbounded interval or integration over asymptotic discontinuity in the domain. So we call type 1 an unbounded interval. Type 2 is over the discontinuity. And I said type 3 is a mixture. So they don't really call it that, but I figured it's worth noting. That could happen as well. So the first step in any of these problems is to replace the improperness with a limit statement. I don't know if y'all's professors require that the first step to be this. I know my professor would count off if you didn't write as a limit initially. So maybe something to consider though, right? Because it's kind of like the improperness is like having infinity in our answer, or in our problem, right? So first we would rewrite the infinity. So after finding, just evaluate the limit. If you end up with a finite real number, we say the integral converges, otherwise it diverges. Okay. So type 1, integration over unbounded interval. This is what it looks like. It could also potentially go from a to negative infinity. It doesn't have to be just a positive infinity in the numerator, or it could go over both, really. Say something like the integral from negative infinity to positive infinity of 1 divided by 1 plus x squared dx. I think that would converge. We know the antiderivative to that function. And then we can evaluate the limits at the bounds, or the bound as a limit. So here I wrote the first step to do, right? It's just the limit as b goes to infinity of f of x dx. So this is type 1, unbounded interval. We're integrating to infinity and beyond. So if we have asymptotic discontinuity, it might look something like this. This is an example of asymptotic discontinuity. So I write it with, limit t from the left now, because we have to consider, coming at it from one side, and then we add the limit from the right to b. Oh, there's a question. I never really understood how writing the limit rather than the integral. Yeah. Yeah, well, so if you have a limit, then you can do L'Hopital's rule. If you have no limit, then that's just, well, you just end up with 0 over 0. Upper limit on, so this b right here should actually be a c. Improper integrals comparison theorem. I don't know if you guys are actually covering. Yeah, I mean, yeah, it's important. It's for sure important because it comes up later in this class too when you guys do sequences, and some of these will diverge that you can't find an antiderivative for. So you would need a comparison test. But if we have two continuous functions, let me ask the group, why do they have to be continuous? And then suppose they're also both positive for x greater than a. Then we have these two statements. So f of x is the bigger function. If the bigger function converges as we integrate, then yes, that's exactly the answer. All continuous functions are integrable. So if the bigger function converges, then the smaller one will have to converge because, right, the integral of the smaller one will be smaller than a finite number. And so that would have to also be a finite number since they're greater than 0. And then they flip it for the next one, right? If the smaller one diverges, then the bigger one has to diverge. Okay, this is just a picture. F is the bigger one. If this red integral from here, all this area, if this area underneath the curve above the x-axis is a finite number, then the area under the blue one will also be a finite number. If the area underneath the blue one is an infinite, is infinite, then the area of the bigger one will have to be infinite as well. And then I made a cool little video. So this is about the rate of convergence of the function 1 over x to the b. So as b is getting bigger, we notice it's converging to the x-axis quicker. However, as b gets bigger, what happens to the convergence along the y-axis? As b gets bigger, it's getting further away, and then it comes back, right? It's really just a bounce, but so yeah. We'll have problems that like discuss or that help us explore the convergence and divergence of these types of integrals. Thank you. How do I get out of here? Okay. You guys can still see. Cool. All right. Oh no. Okay. Well, we're done with integration now. We're going to talk about, in the next 5 minutes, oh my goodness, we're going to talk about the 3D coordinate system. So I guess this would be like a right-hand rule thing. I hate the right-hand rule because I can never understand it, but some people get it. Which of these are the x, y, and z axes? What is the gray plane, and where is the origin? Someone in the chat, help me out. Origin is at the center, yeah, where the red, green, and blue all meet. What is the gray plane? Red is x, yeah, very good. Z is blue, x, red, blue, z, green, y. That's perfect. Vertical axis is the z, yes. What is the gray plane? XY plane, that's exactly it. Okay. Here's a point. I can't remember which point this was, like 2, 4, 2, 2, 4, 1. But you just, you map, right? You would count over, okay, it's 2 right here. And then you count over, like, okay, it's like 5 or 4 over here. And then you make a spot on the x-axis. And then you go from this spot on the xy plane. Did I say x-axis? Yeah, on the xy plane. And then you go up to the height z. Okay. We talk about 3D coordinate system, the sphere. So if something looks like this, exactly like this, or you can force it into this through completing the square, then it's a sphere. Okay. Maybe some food for thought. What if I divide, what if this x divided by h right here was divided by like a, this y minus k squared was divided by b, and this z minus l squared was divided by like c, where a, b, and c were not equal to each other. Almost. It's an ellipsoid. It's a 3D ellipse. Yeah, so you can use your knowledge of conic sections. Very good. Vectors. All right. So two vectors are equal if they have the same magnitude and direction. So these two vectors, they don't start at the same point, but they have the same magnitude and they're going in the same direction, so they're equal. Tip the tail method, they form a little triangle. So let's say we're adding, we would have to be adding this vector right here, and then this vector right here. So like I take this guy. Let's do this. So I take this guy, I put him, his tail is now at the tip of the vector I'm adding it to. And then we complete the triangle. This is the vector sum right here. Okay. So vector scaling. This is when we multiply a vector by a number. If we multiply a vector by a number, c greater than 1, the result will be a stretch. If it's between 0 and 1, it's a shrink. What happens if c is less than 0? It goes the other direction. Let me ask a more advanced question. What if c is less than 0 but greater than -1? Shrink in the other direction. What if it's greater or less than -1? Yeah, it's a stretch. Grows. Yeah, very good. Okay, we have 1 more minute and like 2 more slides. Okay, perfect. So magnitude, we take the sum of the squares and then we square root it. Okay, so you take v1 squared plus v2 squared, v3 squared. Take the square root. Notice this formula still works if we have v3 equals 0, and then that is also which theorem? I didn't ask that very nicely, but so if we're taking the magnitude of a vector, right, and we're looking at the sum of the squares of its components, and we're taking the square root, that's the Pythagorean, yeah, it's like the Pythagorean theorem. So yeah, so vector magnitude in R2 and R3 is the same. And then we have special vectors. These are nice vectors that we like to work with a lot. I, J, K. These are called the standard basis vectors. Um, notice they all have magnitude 1, right? You can take 1 squared plus 0 squared plus 0 squared, that's 1. Then you take the square root, and then that's 1. So these all have magnitude of 1. Notice that these vectors form right angles with each other, and we're not going to talk about anything more with that, but there's some nice properties of them. And then sources. So I guess right now we're going to have a 5-minute break, and then we're going to do breakout groups. I guess I'll be in the main room, and then I'll record. I don't think we can record all of the breakout groups, but I'll record the one in the main room, and then the 2, or I don't know if Les is taking a group as well. The 3 or 4 other leaders will have the students in their breakout group and work these problems that I have provided. So, break time. Do I go to 4? Or tell everyone in 4 to come here? All right, guys. Can you hear me all right? We'll get started in like 2 minutes. Yeah, there was a scheduled break for 5 minutes. Yeah, I tried it. Sure tried. Okay, we're gonna get started now. First problem. The natural log of x dx. So I would really appreciate it if you guys could, if you do have a microphone, to share with your voice instead of typing in the chat, because then I would have to just come back. So how do I solve this? How do I solve this integral? Do you guys remember what section this was in my my PowerPoint? Anyone? Okay. Well, let's remember Lyot. So this is logs, inverse trig, algebraic, trig, exponential. So if I have ln of x, we're going to use integration by parts. We're going to choose u to be the log. And so what's remaining now is dv, but the only thing remaining after we remove this is just 1 dx. So if u is the natural log of x, what is du? And if we have dv, what is v? Can anyone answer what is the natural log? Oh, go ahead.
I can't see the problem that you're working on currently.
Why not?
I don't know.
That's weird. Can anyone else see?
Is it just me? Oh, okay, my bad. I guess it's just me.
Dang. Yeah, try reloading. Okay, so, well, what's the derivative of the natural log of x, guys? If we want the derivative with respect to x, 1 over x. 1 over x what? Dx. And then v. What is the integral of 1 dx? Oh, man. Yeah. Yeah, it is x. So then our formula is u v minus the integral of v du. So this is what I turns out to be. I is just, this is I. I'll use this for I. So this means I is equal to x ln x minus the integral x times 1 over x dx. So this is x ln x minus the integral dx, which is just, well, the integral of dx is just the integral of 1 dx. So this is x ln x minus x plus c. Okay? So number two, the integral arctangent x dx. So this one is another integration by parts. This is integration by parts, and we'll use Lyot. So clearly there's an inverse trig. So that's what we'll choose to be u. So we choose u to be arctangent of x, and du will be the derivative of arctangent of x. What is the derivative of arctangent of x? Someone speak up, please.
Should be 1, and then underneath it's x squared plus 1.
Perfect. Dx. So dv is just 1 dx. So that means v is equal to the integral of this, which is just x. So now we have uv minus the integral of v du is I. This is I. So this is x arctangent x minus the integral v du, x over 1 plus x squared dx. How do we integrate this? Someone raise your voice.
U sub.
U sub. What is u?
X squared plus 1.
So du is going to be 2x dx. But we don't have a 2. This is all right. You just divide by 2. So then du over 2 is, or however you do it, I know there's other methods, is just x dx, which is perfect because we have x dx right here. So this turns into x arctangent x minus 1/2 the integral du over u. So the integral of 1 over u du, or du over u, is ln absolute value of u plus c. So this is x arctan x minus 1/2 natural log absolute value of u plus c. Now we substitute the u back in. X arctan x minus 1/2 ln 1 plus x squared plus c. Why doesn't it matter that I don't have absolute values?
1 plus x squared can never be negative.
Yes. Yes, 1 plus x squared is greater than or equal to 1 for all x. Okay, so now we're on to 3. Let's see. I'll skip number 3. We'll go to 4. It says, first make a substitution, then use integration by parts to evaluate this integral. So what should I make a substitution for? This is a trickier one.
Negative theta squared?
Yeah, that's okay. That's okay. So I'll do t. I'll use t because we'll have to use integration by parts eventually. And I don't want to use u twice. So we could do negative theta squared. We could also do positive. It doesn't really matter. I'm going to choose positive because that's how I have it in the solutions. And so let's rewrite this first, though, as theta squared e to the negative theta squared theta d theta. And then after this, I hope it's clear that dt is 2 theta d theta, which makes this 1/2 dt is theta d theta. So now we have theta d theta, and then we have t being theta squared, and we have that in 2 places. So now we can make the substitution, right? We have 1/2 t e negative t dt. How do I integrate this? So this is integration by parts, with u being, remember Lyot, and then dv being so u, we would choose algebraic because exponential comes after in the order of precedence for u. So we use t for u, du is just dt, dv is what's remaining, e negative t dt, and v would be negative e negative t. So in general, let's say k is non-zero, then the integral of e to the kx dx is 1 over k e to the kx plus c. This also works for sine and cosine. Okay. So then we use our integration by parts formula. So we have uv negative t e negative t, right, the 1/2, of course, minus the integral of v du. This double negative, so this turns positive, the integral e negative t dt. So we integrate this once more. So this would be 1/2 negative t e negative t minus e negative t plus c. Are we done?
No, you
No,
have
you
to
have to plug
go
that
back.
in.
Yep, we have to plug it back in. We made a substitution. So 1/2 negative theta squared e negative theta squared minus e negative theta squared plus c. Okay. Okay, we'll do sine squared. Sine or cosine? Sine squared. So whenever we have a sine squared by itself or a cosine squared by itself, all we have to do is the power reducing or double angle formula. We just use this and then integrate directly. So this is going to be 1/2 1 minus cosine 2x dx. This is 1/2 x. What's the integral of cosine of 2x dx?
Would it be 1/2 sine 2x?
Yeah, and it retains sine. Okay. So what we can use is the integral of k or cosine kx dx is 1 over k sine kx plus c. I think k cannot be retained sine. Yeah, I guess, I mean, doesn't it? So yeah, the integral of cosine retains is sine and retains sine, isn't it? So k cannot be. I was just thinking of what if this was something that made cosine 0. So if this was like odd multiple of pi over 2, then this would just be the integral of 1, and we would have a different formula. So in most cases, though, if k is not one of these, then this is the formula we would use. So 6, this is exercise for you. Write this down on your paper. Try it later on your own. Use a similar formula to this, or you could try it right now real quick. Who knows? Okay. All right, let's do tangent. We talked about this one, right? So this is 7, the integral tangent x dx. So first, convert to all sine and cosine. Well, there's only like one thing to convert. Then we're going to choose u to be cosine x, so that du is negative sine x dx. So this means negative du is sine x dx. So we have negative integral 1 over u du. We already said the antiderivative of 1 over u is ln absolute value u. U is cosine. Add c. Okay, now we use the power property of logarithms. P ln of anything is equal to ln that thing raised to the p. So this is ln absolute value cosine x to the negative 1 plus c. But cosine x to the negative 1, that's just secant. Because this is really like 1 over cosine. So this is ln absolute value secant x plus c. Okay. So
Would both
7.
answers be accepted on the test or just the simplified one?
I would put the simplified one. This is how it's written in most books, or like everywhere I've seen it. Like at this point, really just memorize it. Like you have the integral of tangent now. The integral of, so like put like a integral of tangent x dx is always ln secant x plus c. So you can just memorize it. I have it memorized. So this is what, 8? Exercise for you. Yeah, that's right. Cotangent x dx. Try this one. Try it for yourself. Similar method. Okay, now we get into the magic. This is truly magic. I would have never been able to think of this in a million years. This is where I said the magic one. So we can multiply anything by 1 and get that thing back out. So I'm going to multiply this integrand by 1 in a special form. So it's called a secant x divided by 1. My magic one is going to be secant x plus tangent x over secant x plus tangent x. And we have our dx, of course. Now I'm going to distribute this secant through. So we have the integral secant squared x plus secant x tangent x over secant x plus tangent x dx. Now you're probably thinking, well, that looks a lot more complicated, man. But if we use u as the denominator, then du is exactly the numerator in a slightly different order. All right, we just have to commute. Right, we have a secant squared, we have secant squared, secant x tangent x works out perfect. Dx, dx, awesome. So our integral in u, 1 over u du. We can integrate this ln absolute value secant x plus tangent x plus c. Done. Memorize it. You can use it later. Okay, number 10. Exercise for you. The integral of cosecant x dx. Another magic one. Try it for a minute. You might find it. And then you can verify your answer on an integral calculator or look up the solution online. Now we're going to use integration by parts to evaluate secant cubed x dx. Okay. So we know that cosine x plus sine squared x equals 1. If I multiply both sides of this equation by 1 over cosine squared x, I would hit it here, here, here. 1 plus tangent squared x equals secant squared x. That's how you get that formula. Okay. So we can write this integral, if I can remember how to do it properly. I think we're going to do secant x, secant squared x dx. So then we do well, we can integrate secant squared x just fine. So I'll use integration by parts. I'll choose u to be secant x. du is secant x tangent x. dv is secant squared x dx. V is, hopefully this works, tangent x. If not, I'll look at the solution. So we have u v minus the integral of v du. And then we know tangent squared is secant squared x minus 1. So I'll just replace this. Yeah, this is going to work out fine. So we have I is equal to this. So I equals secant x tangent x minus the integral secant x secant squared x minus 1 dx. Distribute. I is secant x tangent x minus secant cubed x dx plus the integral secant x dx. What do I do now, guys? It's the same thing in here as what we started with. Is that bad? Is that okay? Very bad. It's not bad, actually. So I call these boomerang. Because it like comes back to an integral that we're already working. So initially, if we call this I, then this would be like having a negative I. We already have I right here. So we have I equals secant x tangent x minus I plus, and then what's the antiderivative of this? Well, we just found it. This is plus the natural log absolute value secant x, plus tangent x plus c. So we can add I over and collect them. So we have like 2i equals secant x tangent x plus ln absolute value secant x plus tangent x plus c. So then I is now 1/2. We just divide, right? It's a multiple of the integral we started with, so we can isolate it. Okay, and now the c didn't change, really. I mean, we could call this c1 and c2. But if we have a constant, we divide it by the number 2, then it's just going to be a different constant. So let's say, therefore, the integral secant cubed x dx is equal to 1/2 secant x tangent x plus 1/2 ln, all this business, man. Okay. We have a pretty good pace going, so I guess we can do number 12. Am I matched up? Yeah, I am. So number 12, secant to the 5th. And the hint is use integration by parts and the answer from the previous problem. Okay? So let's do u is, and then dv is something. So I think if we use dv, if we use dv to be secant cubed, then we would have to integrate v du, which would actually be an animal to solve. Here, like I'll show you. Like if we had this to be dv, then v would be this guy. And then in our integration by parts formula, we would have to integrate, well, this guy times du, and then that would just be a monster. I wouldn't want to do that. So so let's try like integration by parts on something else then, or maybe it's something with peeling off a secant squared first and integrating it. So let's try that. Yeah, that's what we did last time, isn't it? So if we choose u, well, first let's rewrite it. We have the integral secant cubed x secant squared x dx. So dv could be secant squared x dx. So v is simply, oh, nice tangent, right? That's nice. And so this is secant cubed x. What's the derivative of secant cubed x? Someone? Someone calculate it. Tell me the answer.
Would it be 3 tangent secant squared?
Oops. Let's see. 3. Maybe 3 secant cubed. Is that what you said? Wait, times just one tangent. Someone get it in the chat. Secant cubed tangent. Yep. Okay. Yeah, so this guy. I hope that's what you said. Okay. And then we use integration by parts, uv minus the integral of v du. So we have uv is just secant cubed x tangent x minus the integral, minus 3 times the integral v du tangent squared x secant cubed x dx. What do you guys think we should do now? We reduce the power of secant. Did you get something different? Did I get something different? I don't know what you mean. Is this right, someone? Anyone? Does this look right? I think it's right. So maybe we try another round of integration by parts. So no, we don't. I know what we do. We use secant squared x equals tangent squared x minus 1 right here. Why? Well, because when we replace this with secant squared minus 1, we'll have negative 3 secant to the 5th minus secant cubed, integrating that. It's a boomerang because we have secant to the 5th again, and then we also know, we do know the integral secant cubed now from the last problem. So that's what we're going to do. This is I. I is secant cubed x tangent x minus 3 secant squared x minus 1 secant cubed x dx. Distribute minus 3 integral secant to the 5th, the boomerang part, minus plus secant cubed x dx. Of course, this guy, oops. This guy tags along. Now we just collect the I. This is I right here. We collect the I, so we have 4I equals secant cubed x tangent x plus 3. And then the integral of secant cubed x dx, 1/2 secant tangent, secant plus ln secant plus tangent. Now we divide by 4. 1/4 secant cubed x tangent x plus 3/8 secant x tangent x plus ln secant x plus tangent x plus c. Yeah, that's right. Okay. Okay, so that was 12. Let's say, let's do 15. Prove that this integral is 0, where m and n are integers. All right. So you guys will have the problem list. We'll get that somehow. It'll be definitely on the YouTube video, the description for the YouTube video. So you guys can work some of these other problems. I just need to get through sine mx cosine. I need to touch on, like, you know, the main ideas of these. And then we want to show that this is 0. So this is multiple angle of the product, sine and cosine. M and N are integers. So what do? We use this formula. Well, let's just use a plus for now. So this is going to be sine mx cosine nx plus cosine mx sine nx. We should know this from trig. And then we also have sine m minus n x equals sine mx cosine nx. It only varies by sign. Cosine mx sine nx. So if I add these two, then these will eliminate. Right here we get twice of our integral. So that means that sine mx cosine nx is equal to 1/2 sine m plus nx plus sine m minus nx. So we integrate, right? We're integrating this. This integral is this integral. And then we can solve the right-hand side integral very easily. So we want to show that this is 0 for integers m and n. So we have I equals 1/2 integral sine m plus n x dx plus negative pi to pi sine m minus n x dx. So remember, if we have sine of k x dx, this is 1/k negative cosine kx plus c. So then we integrate this one and this one. First, let's assume if m is not equal to n, then I turns into 1/2 negative 1/m plus n cosine m plus n x minus 1/m minus n cosine m minus n x. Okay. So now we can plug in our bounds. So cosine of m plus n, well really, let's call it like this. Cosine of k times pi. Oh, now it's like odd and even. Do I have to break it up like that? I'm getting stuck. What did I do in my solutions? So it's 15. I just said it was 1. But I guess it could be positive or negative 1. Oops. Okay. Well, you get the general idea, guys. So I guess if m and n are not equal and m plus n is even, and then I think this would also imply that m minus n is even. So like either they're both even or they're both odd. I didn't think about that too much. That might not be right. So if they're both even, cosine of k pi is 1. So then we would have 1/2 1 over m plus 1 or m plus n times 1 minus m minus n times 1 minus a negative 1 over m plus n times 1 minus 1 over m plus n times 1. So this negative, double negative makes a positive. It's the same thing everywhere. Here, here, here. So these all cancel. So this equals 0. Otherwise, right, if these were not both even, then they would be both odd. And in which case, we would have cosine k pi equals -1. But the same thing would still hold. Maybe that's exercise for you. Okay, so this is if m and n are not equal, but if m equals n, then this integral would be sine of 0. Sine of 0 is 0. So if m equals n, we only have the integral on the left. So then we would have I equals the integral 1/2 negative pi to pi 1 over m plus n sine m plus n dx. So this is, oh wait, not that guy yet. So this is 1/2 m plus n cosine negative m plus n. Oh, I forgot the x. X evaluated from negative pi to pi. So this is -1 over 2. Same deal, right? Same deal. We just have one less of them. Either there's gonna be both 1 when I evaluate them here, or they're gonna be both -1. And then since we have to like do f of b minus f of a, we get that this guy is 0. So I'm sure you guys don't want me to bore you with this any longer. I could go more into it, but so therefore this integral is 0 for all m and n integers. And so we go on to exercise for you. Right, so you guys can see my screen, so you guys can write down these 16 and 17 integrals just for time saver. I don't have to copy and paste it. So yeah, so this integral of sine mx sine nx, it's 0 when m is not equal to n, and it's pi when m equals n. And then actually it's the same formula for 17. It's 0 when m does not equal n, and pi when m equals n. So now we can do number 18. So 18 is a trig substitution problem. we have the integral of dx over ax squared plus b squared to the 3 over 2. So first, I'm going to factor out an a squared out of this denominator, both terms. And so I get a squared x squared plus b squared over a squared. I'll just call that b over a whole square. And then this is all raised to the 3 over 2. So 1 divided by a squared to the 3 over 2 is just 1 over a cubed. So this is 1 over a cubed, the integral dx over x squared plus b over a squared to the 3 over 2. Now this is trig substitution. What should I choose for my x? Anyone?
A tangent.
Yeah. It would actually, in this case, it would be b over a. And then that means dx is b over a secant squared theta d theta. So now we can go ahead and substitute. So we have 1 over a cubed. Dx is b over a secant squared theta d theta. X, we square it. We have b squared over a squared tangent squared theta plus b squared over a squared to the 3 over 2. So we can pull out a b squared, a 1 over b squared over a squared with the 3 over 2. So we take the square root and we cube it. So this would be a cubed over b cubed. Okay. And then remember, we have a b over a right here. So this is really trying to keep track of everything. We have 1 over a cubed b over a times a cubed over b cubed, the integral secant squared theta divided by tangent squared theta plus 1 to the 3 over 2 d theta. So the b power of 2, a power of 1. Is that right? Is that right? Let me see. Here's 18. Yeah, that's perfect. Okay. So this is 1 over ab squared. And then the tangent squared plus 1, that's just secant squared. But we're taking it to the 3 over 2. So just in case anyone's not following this, this is like square root of secant squared theta to the third. So this is like secant to the third theta. All right, it's basically like the 2's will cancel. And then so we have secant squared theta over secant cubed theta d theta. So this is now just ab squared. This is secant, 1 over secant, but 1 over secant is just cosine. So cosine theta d theta. Now what's the antiderivative of cosine theta d theta?
Just
Does
sine
it
theta.
retain sign, or is it? Someone say something?
Yeah, it should be sine theta, right?
Yep. Okay. Now we need to use our triangle. So our initial substitution was theta. We had this guy. X is b over a tangent theta. So ax over b is tangent theta. So opposite, adjacent, sum of the squares, Pythagorean theorem. Now we want sine, opposite over hypotenuse. So this is 1 over ab squared, opposite over hypotenuse. Oops. And then the a's will cancel. So this finally is x over, this is 1 over b squared x over ax squared plus b squared plus c. And I think this is it. Oh, I got a negative somehow. Oh, what the heck? Messed up. Negative cosecant. 1 over sine. So there should be a square in the denominator. Did I write down the problem incorrectly? I think I did. Yeah, I did. Wow, I did a different problem. Okay, well, so you see, guys, there's a positive how I wrote it down, but on the problem list it has a negative. So I assume what I did was right. I mean, all this looks correct. So I guess you got like an extra one. So you guys will have the other one posted on the. Thank you. Yeah. So then, so this, I think this is the right answer to our problem. And then how would you check? Well, you could differentiate, or you could just plug it into a calculator, right? Okay. So use trig sub to show that the integral of dx over the square root of x squared plus a squared is this natural log business. Ignore 20. We didn't cover the hyperbolic stuff, so you guys can ignore 20. It's just it seems like a more straightforward way to solve this integral. So up to writing down the problem correctly, seems like we're doing pretty good. Okay, we got the integral of what dx over square root x squared plus a squared is check. Okay. So this would be trig sub, obviously, right? It's a square root, and then we have one of the three forms. So x is equal to a tangent theta is our form. So I'm going to calculate dx, which is secant squared theta d theta. So this turns into a secant squared theta d theta over a squared tangent squared theta plus 1. So this is, well, the a's will cancel, right? We're taking root a in the denominator, so that turns into a, rather, absolute value of a, 1 over a, and we're multiplying by a to begin with, so the a's will cancel. So this is secant squared theta, secant theta d theta. Right, tangent squared plus 1 is just secant squared. We take the square root, that's secant. So now we have the integral secant theta d theta. Okay, well, we know this. We know this one. This is the natural log, absolute value, secant theta plus tangent theta plus c. So tangent theta is x over a. So our triangle turns into Theta, opposite, adjacent, Pythagorean theorem. Secant is hypotenuse over adjacent, SOHCAHTOA. Right, the ka is associated with cosine, secant is associated with cosine as well, and so we just flip the order of these two. So secant is hypotenuse over adjacent, which is ln the square root x squared plus a squared over a plus x over a plus c. Now, we can factor out a 1 over a. Then we can use log properties. We know that the natural log of something, I'm not going to do that. We know the natural log of x times y is the natural log of x plus the natural log of y. So we're going to do that with the 1 over a and then this guy. So this is natural log. I think we can assume that the argument right here is positive. So we can drop the absolute value. We can assume this because of the domain, or rather, I guess, yeah, it would be with the domain of secant, because that was our substitution, or tangent rather. But also in the problem that I got from the book, this is how it was listed. So it didn't have any absolute value. That's why I think I can kind of give it without reason. Yeah, so I think a or at theta would have to be in between like 0 and pi over 2 to make x positive. So I guess whenever we're doing a trig sub, this kind of, we can only do this for theta in between 0 and pi over 2 to make x, and then x would be positive as a result. So we can drop the absolute value. And then ln of 1 over a is just a number, so we can combine that with c. So this is finally the integral is x plus x squared plus a squared plus like c1 as required. So okay, we have 10 minutes and not getting very, we're not going to get to all of it, man. Okay, let's do 23. Now let's do 22. Let's do 22. E to the x, 2e to the x, 3 over e to the x plus 1. For 23, this is improper fraction. And then you would just do polynomial long division. And then you would do, then you would just integrate, right? I think it's pretty straightforward how 23 is. And so we'll do this 22 e to the x over 2e to the 2x plus 3e to the x plus 1. Okay. So let's first make a substitution. Let's do u is e to the x. Then du would be e to the x dx. Ah, perfect. That's in our numerator. So that's du, integral du. Now, if u is e to the x, u squared is e to the 2x. So we have u squared plus e to the e times u plus 1 with a 2. And so this factors, doesn't it? Sure hope so. Otherwise, we would probably need to complete the square in the denominator. But if this factors to be, yeah, this works because we have 2u squared plus 2u plus u, that's 3u plus 1. Yep. So then we would do partial fraction decomposition. I I said I wasn't going to do it, but I'm going to actually do it. 1 over 2u plus 1, u plus 1. This is a over 2u plus 1, right? This is non-repeating linear. And so this is plus b over u plus 1. Then we multiply this guy by our common denominator. This is 2u plus 1, u plus 1, so that this will cancel over here. We have 1 equals a times u plus 1 plus b times 2u plus 1. So this is a simple solving technique that we can use. If we let u, since u is a variable, we let u be -1, for instance, to cancel this one. We plug this in right here. So this one would be 0. And then we have 1 equals b times -1. B equals -1. And then we let u be whatever it is to make this term 0. So that would be u is -1/2. And this means that a would be 2. And so now our integral turns into 2 over 2u plus 1 minus 1 over u plus 1 du. And now we can integrate. How do we integrate this?
Natural log.
Yeah. You have to account for this guy, but he would cancel with him. So this is natural log, absolute value 2u plus 1 minus natural log u plus 1. It's really a u substitution, but this plus 1 doesn't do anything with the u sub. This 2 would affect it, but it cancels with the 2 in the numerator. And so this is finally natural log 2e x plus 1, always positive, right? Minus ln e x plus 1 plus c. Okay. Now I guess we're on improper integrals. Okay, we'll do 25. -2 to 3, whatever x to the 4. So this had to do with that video that I showed y'all of the convergence of or really it just set the 1 over x to the b. It set the b as the parameter and showed all the different graphs. And we got to see how it got squished in various directions while we changed b. So this is in the special case, b is 4, right? So this is improper integral because there is discontinuity at x equals 0. So the graph looks like this, from -3 to 2. So we want to know if this area is finite. So I'll just look at one side. I'll just look at one side of it. I'll do limit t approaches 0 from the left, -3 to t, x to the -4 dx. This is limit t approaches 0 from the left, -1/3 x to the -3. Add 1 to the exponent and divide by that number. -3 to t. So this is -1/3 t, or 1 over t cubed. Triple negative is -1 over 3 to the 4th. Take this limit. This limit, is it finite or infinite? Really, I kind of wrote it sloppy, so I'll rewrite it right here. I'm asking about this limit. So as we approach 0, we're dividing by a really small number, really small negative number, or a negative number that's close to 0, right? So this blows up. Actually, this is infinity, or equal to infinity. So this is equal to infinity. Therefore, if we have like one side diverging, then the whole thing diverges. Therefore, I diverges. Okay. I guess we'll touch on the 3D coordinates. So it says find the equation of the sphere's multiple with center 2, -3, 6, and there's 3 cases. One that touches the xy plane, yz plane, and xz plane. I feel like everyone's leaving. So we want a center at 2, -3, 6 sphere. And well, just starting from here, we know the basic form will be like x minus 2 squared plus y plus 3 squared plus z minus 6 squared is r squared. And so now it's centered at the same point. The only other parameter that we have is r. So let's kind of draw a picture. We have 2, we have -3, and we have 6. Okay. So if we want it to touch the xz plane, it's like this guy. What would his radius have to be? How far is he away from the xz plane?
Is it 3?
That's right. Yeah, so he counted just the x, right? Because we want x to be 0 when it touches the xz plane. So for xz plane, r is 3. Now for the xy plane, someone else, what would the xy plane be? The radius for that associated with the xy plane, that's the one on the ground. How far are we away from the xy plane? The xy plane is where z is 0. Okay. Well, or maybe the person who answered the last one, you see? What do you know what r would be? Yes, it would be just 6, right? The distance from the center to the xy plane. And then for the yz plane, that would be
2.
Yeah, it would be 2. That's when x is
Okay.
0. Yeah, perfect. R would be 2. And so you could just plug in these R values and answer them separately or whatever. All right, guys, that's 9 o'clock. That's all the problems I'm going to do. We'll get this, the description, the solutions in the description and everything. So thank you for joining me.
Thank you.
Yeah.
Thank you. Have a great night.
Yeah.